Okay, before we get started, are there any questions, concerns? As there, yes? No? Everything copacetic? Okay. There's a for those who like to kind of work ahead, I did post the next computer assignment. It's going to use something I'm going to talk about today, which is called sim event listening. So after today, you should have all the stuff necessary to be able to work through it. The written assignment, which is due at the end of the week, is the thing about that is that it's two different formulations of the multiple server queue. So we've seen one, and the point that that's trying to illustrate, among others, is that there's no one way to necessarily to formulate a particular model. For a given model with a certain set of requirements, there are many, many wrong models, and there are typically a few more than one right, quote, right model. And what makes the model right is not that it's the be all and end all. And there you can kind of get into VVNA, verification, validation, and accreditation, that whole thing beyond the scope of this particular class, but nevertheless an important one. What is powerful about the relationship between event graphs and the code, whether it's in SimKit or DeskPy, is that the verification piece is fairly straightforward. In other words, the event graph, when fully blown, is in fact the design document for the model. And so verification, which is does the simulation instantiation, does the simulation program do what it was designed? In other words, match the design. And for this, that's a very low bar. Or, I mean, in the sense that if you have an event graph and it has been the translation into the code is literally a one-to-one. It's not programming, it's just translating. And in, I think it's section 8, but I'll have to do, there's effect on the, I'll post a separate handout of this, but there's basically the Rosetta Stone for SimKit at least. There's one for the Python version. I'll have to dig her up. But for every element of an event graph, there's a corresponding element in the program. So as we've already seen, events translate into methods. Scheduling edges translate in SimKit into wait delay statements. In the Python version, they translate into a call to schedule. Okay, so why the difference? Well, because when I wrote SimKit back in the day, I've since come to realize that some of the terms that I used were not ideal. So by the time I realized that, there were many applications that kind of used the existing one. And if you've ever updated an application and all of a sudden everything that you had before broke, I mean, that's something that I experienced and didn't want to foist upon folks. So I'm kind of stuck with the terminology in SimKit. When I wrote the Python version, I had an opportunity to make it a little more consistent with the words. But nevertheless, each of the piece of an event graph corresponds directly to a piece in the code. And so, in other words, you can sort of almost hand verify the thing. Now, validation is another matter entirely. So verification is, did you implement correctly? Validation is, was it the right model in the first place? And what I hope you're getting a little bit of a sense of is that modeling is an iterative process, and the meta approach that I'm recommending to you is to start with simple models and then identify the areas where they don't capture the elements that you want, and then upgrade the, well, how to upgrade those. Well, I like to take the quote optimal test taking approach, which is choose the easiest ones first. And one of the reasons for that, if I could sort of stay on my soapbox for a few more moments with your indulgence, not that you have a choice, but the thing is this, is that if for some reason you find it impossible to create a simple model that represents at least some of what you're doing, if you can't do that, then what hope do you have for implementing the complex things? I mean, that's something that not a lot of developers sort of realize. In other words, I mean, without pointing fingers or naming names, there have been some spectacular failures in DoD simulation where they tried to model the whole world and for some reason fell short. So, start with your house and then see if you can do the whole world step by step. So it's, what is the cliche about eating an elephant one bite at a time? So just start with small bites and then move out, and your mileage may vary. So okay. So, and again, let's see if I can get this right here. Okay. Oops. There we go. Hopefully everybody can see this. It claims to be sharing. Okay, so today we're now going to extend the tandem queue that we talked about the other day into what I call the transfer line, and then go into this sim event listening idea and illustrate it with something called the simple server component, which you're going to implement. So this listening idea is a very powerful one. And what's powerful about it is that it allows what I call loose coupling, or I'm not the only who calls it that, but it allows you to take components that you've built and then kind of hook them together to build models that go beyond what you may have originally intended. And it's sort of fashioned after the fact that as computers have evolved, the type of connectivity that you have has, well, a lot of it has kind of moved towards various forms of USB, universal serial bus. But back in the day, you had all kinds of different connectors and all kinds of different things. So it's like if you had two devices, and conceptually they could work together, but there wasn't a way to actually literally hook them together. Nowadays, we kind of take that for granted, that if I have a device, I don't have to worry about can I connect it to my computer? Why? Because almost everything is a USB. So if it's some form of USB, it can work. So, but software doesn't work that way. And this listening idea is kind of the closest that I've been able to come to being able to capture some of the elements of that. In other words, if you have two sim entities, then they can listen to each other without, and that's part of the design. Anyway, so we'll get into that. All right. Okay, so what is the transfer line? So And this is another kind of illustration of what I was talking about. So we started with our multiple server queue, and they said, well, what if we don't leave the system, but we go to another queue? So that became the tandem queue. And then, of course, the next logical thing is, well, why stop at two? Why not have more? And if you look at any kind of check-in system that you've probably experienced, where you kind of go to one thing and then another and then another, DMV, just a lot of systems are kind of like this. Even some fabrication systems are like this. This is superficially, you can sort of think of an assembly line. What's different is an assembly line is kind of forced. Basically, everything's kind of moving, and that there aren't really any queues, as it were, which causes problems, by the way. What the tandem, what the transfer line is, means that you have these workstations, and then you process something at that workstation, and then transfer it to another workstation where some other task has to be done. In many fabrication shops, that's the sequence that a typical part will go through. This is the way it's organized. So you'll start with some bare metal, and you start manipulating the metal in various ways. Drilling, shaping, grinding, welding, etc. And in what's called a job shop, the route through those various machines kind of goes back and forth. With the transfer line, there's always just a given sequence. That's just what it does. So each job is processed by a series of workstations in sequence, and each of these workstations is a multiple server queue. So this is a generalization of that. And now there are, with this listening idea, we can actually take instances of a multiple server queue and kind of hook them together to do this. That's one approach, but we're going to take another, and it's to illustrate using arrays as state variables and parameters. That's kind of the part of the example. So what are the elements of this? Well, one is we're going to assume that we're going to have some kind of arrival-like process for the arrival of these jobs. Again, that's an assumption which we may or may not, it may or may not hold for a given situation. So, but the situation we're modeling, we'll assume that that's going to hold. A natural generalization of this would be a job may arrive, but a job may have multiple jobs as part of it. So like we get a job that might have, like, say, 10 items that need to be processed for this job. But here we're just going to do onesies. Now parameters is, for some reason, I seem to have a random process between calling M and N, the number of workstations. So depending if you downloaded the slides, if you did them earlier than about 20 minutes ago, it'll probably say N, but I changed my mind to M. Why? Only my therapist knows for sure. Okay, so now here's the thing is that at each workstation, you're going to have a different number of machines. And so kind of informed by our multiple server queue, we're going to call that K, but now we're going to index it by the machine. So K sub I is the number of machines at workstation I, and we're going to use the silly zero-based indexing. Why? Because if we formulate it that way, then the translation into the code is straightforward. If we do it the same way, which is to start with one, then when we try to translate it, then we have just some bad choices, and regardless of which poison you pick, there's going to be an off by one error at some point, guaranteed. And it's not your fault, it's not my fault, it's the fault of the people at Bell Labs back in the 1960s when they wrote C. So you can blame them. Okay, so now likewise, each workstation has a different service time, but all of the machines at a given station have the same distribution of service times. That's just like that. So these are the parameters. Now, the state variables, we're going to have sort of a bare bones one. We could augment this if we wanted, and I'll leave that to the interested reader. And here again, this should be M. I'll have to fix that as well. I don't know. I just sort of get these random. Which one is right? Should it be N or should it be M? M for machines, N for number of machines. Okay, so, all right. So again, informed by our multiple server queue, we're just going to index it, the number of queue in the queue at station I. So that second part is important. And the number of available servers at station I. So just like the tandem queue, we need a different state variable for each station. And the terminology, we're going to use station as a term. So a station is going to be a place where there are multiple identical machines or servers, if you will. And the number that we have at each is going to be different. And the amount of service time at each is going to be different. And likewise, the state variables, the number of available machines at each station is going to, just sort of vary. Okay, so those are the parameters in the state. We might be interested in more, for example, like what's the total number of machines in the system at any point in time. We could time permitting, I'll show you how to augment it with that. Okay, so now for this now, when creating an event graph like this, there are basically kind of three elements that we want to consider. And I want to take you through those because when you're, as I say, like this first written assignment is a very straightforward one, but as we go along, I'll be asking you to do more and more complex models. And so this is kind of a template, if you will, for kind of how to, in other words, the template is first define your parameters and state variables. And then when doing the event graph, if it's fairly straightforward, it's a very simple one, as I'm asking you to do, then you can just kind of go ahead and do it. When it's a little more complicated one, then I'm going to break it down into three pieces and then put the pieces together. So one is modeling the arrivals. The second is initializing the array state. So far, all of our, here's the conundrum. As I said, even though in code we can do it, in pure event graph modeling, we don't have a for loop. So we have to do something a little different. And well, what do we have? We have the for loop that we talked about yesterday. So that's what we're going to be using. And then the main logic, which is kind of how things go once we actually get going. So modeling arrivals, we've already kind of done that. So the piece of the arrivals would look something like this. And this is just a piece now. This isn't the full model, but this should look familiar. This is our old friend, the arrival process, which is actually, my favorite model. Why? Because it's so simple and it's actually quite useful. In fact, we're going to see at some point that once we start componentizing things, that is an extremely valuable component for certain situations. For some situations, it's actually not appropriate. And we'll see what some of those are later in the course. Okay, so initializing the array state. So that's where, if we were doing, if I say, here's an array, now think in terms of code, whatever your favorite programming language is. And I have an array and I want to initialize the state of that array. What would you do? You'd write a for loop. If I had an array of the initial values, then I would initialize it by looping through a for loop, and for each index, set it equal to the right value. Now, in pure event graphs, we can't do. In other words, if I could write for down here, then that's what I would do. But I can't do that. But I do have this for loop. So this should look familiar. This is what we did yesterday. And this is one of the use cases for this. So every time init I gets executed by the event list, we will set the number of available servers at that station I to ki, the number there, and we'll set the number in the queue to 0, because those are our initial conditions. So instead of putting it all into the run event, we're gonna use this structure. And unlike run, init is just kind of that's just kind of what I've used. And then when, of course, I went to Python, and it is what they use for the constructor, so that may be confusing, but if you're careful, there's really kind of no issue there. Okay, so we have we've captured the arrivals. We can initialize our array states. So whenever you have states that are arrays, then they need to be initialized. This is the way to do it. And then finally, the main logic for the events. Now, informed by our multiple server queue, we would pick a state. So in this case, what our state is the array queue, but like, what does this represent? Arrival. Now, this I is an argument. And yesterday we talked about how to do arguments on events. And so when arrival I happens, then that will increment the number in the queue at station I. So this will be the ith element of that array. Now that illustrates an important feature of events. And here's where kind of thinking of them in terms of methods is useful. Everything that an event does, which are state transitions and scheduling, it has to know about. And if you think about writing a method, whether Java or Python, that method has to have access to every variable that it's utilizing. So now, like states are implemented as instance variables, and correspondingly in event graphs, all events have access to all states. All events have access to all parameters. And that's, in a way, that's why both states and parameters are implemented as instance variables in both Java and in Python. Okay, but here's the thing. So what state variable does this event have access to? It has access to the array queue. The array queue. How does it know what the value of I is? It gets passed. In other words, somebody tells it. And how do they tell it? They tell it by passing it. Okay, so every event, you need to make sure that you're using things that you have access to. If I didn't have this here, if this were just an arrival event with the 0 arguments, then this would not work. And unfortunately, there's no compiler for pencil and paper things. So if you were writing this in code, then the compiler would give you a red squiggly. Why? You know what the array is, but you don't know what I is. And so, let's erase everything. Okay, so we know that I is, and so that you always need to, just as a check, does this event, the state transitions, refer to everything that is accessible? And there are 2 ways that an event can know about a variable, just as in the programming language. One is that it has access to an instance variable, in this case the array, or it's an argument that's been passed in. So start service, same thing. Okay, we have a parameter I, and we decrement the number in queue at I, decrement the number of available machines at I, and likewise end service I, we increment the number of available servers or machines at I. Okay, so we have, and we've already done the run. Okay, so this is still all part of the model. So next would be the scheduling, and well, I tell you, let me do it from here, just to kind of show you. All right, so an arrival may schedule a start service event, but under what condition? Under the condition that there's an available server at that machine. So if there's an available server at some other machine, but not this one, then this is going to be false. So does the arrival event know about the array S? Yes, it's a state variable. Does it know about the index I? Yes, it was passed in, so we can do that. Now, so as it sits, this is now syntactically incorrect. Now, can you see what is missing? The scheduling edge is not correct. It needs the argument, exactly. We need to pass it in. So what do we start service on? We start service on machine I, or the station I. So we pass that in. Remember that the arguments are the little box here. Don't confuse these with the delay. The delay is something without a box. So the parameter is inside the box. The delay is outside the box. So think outside the box. So similarly, a start service would schedule an end service with a delay, always with a delay of a service time at station I, because they're all different. And we need to pass the station that we're at. In other words, a start service at station I is going to schedule an end service at that same station. And similarly, when we end service at a particular station, then if there's somebody in the queue at that station, then we schedule a start service at that station. Okay, so now, assuming that everything else is kind of hooked up, where would we kind of start? Well, we would have to at some point have an arrival at station 0. And then at some point it would, if there was a server, that first guy is going to schedule a start service at 0. And that's going to schedule an end service at 0. And when that happens, it's going to schedule another start service at 0. But what's missing? Yeah. So when we're finished at one station, how do we move on to the next station? Well, what is showing up at the next station? What is showing up at any station? That's an arrival. So, in other words, now if I'm finishing service at station I, what's the next station? I plus 1. And rocket science here, but it's okay. So in other words, now I'm going to pass I plus 1 to this arrival. Now, am I always going to do it? No. I'm not going to do it if I'm the last one. So how do I know I'm the last one? Now, it turns out that I have to, and this is something, should it be I less than M or I less than M minus 1? Turns out I less than M minus 1. Just like in the event graph for loop, is I minus 1. So here's hopefully I got it right. Okay, so these are the 3 pieces. We have and then putting them all together looks somewhat like this. And I hope you can kind of, how should I say, if I just threw this up, then it kind of looks a little bit like a plate of spaghetti, even just with these few events. So, but here are the pieces. Here's the initialization of the state variables. Here's the arrival stuff, and here's the main thing. And the one piece that is now that needs to be added, though, is that what happens when we have an arrival. So when these arrivals are kind of churning along, but when one of these comes up, we want to schedule an arrival at that first workstation. The first workstation has an argument of 0. And so every arrival event without an argument is going to schedule an arrival passing the value 0, meaning that it's going to be the first one. So that's how the thing gets kicked off. And just as another check, there's a directed path from every run event to every other one. So they stand a fighting chance of doing it. That doesn't mean it's correct. That means it's not incorrect. Okay. Now, and actually, in a way, this is a little bit of motivation for what is coming next. And that is when when these were invented, as it were, they were extremely, they were just fantastic, at least, according to those of us who used them. Why? Because, even as complicated as this is, knowing what the pieces are, you can look at this and actually, without even running a model, you can kind of see what this thing is doing. There's a lot of understanding of what this is about, because these graphs are very visual and very, very visually compelling and very visually informative. So, I mean, this is orders of magnitude more informative than code. If when you look at, and at some point I may ask you to implement this, but when you look at the code, it's like you can't tell what the heck the thing is doing. But you look at this and you have a sense of how this is going to act, and that's very important. Okay, but I think you can start to see some of the downside of this is that as models get bigger, we've been looking at very small models. So even for a relatively small model, this is getting a bit busy. So when you look at how this was kind of built up, there was this arrival piece that was there. There was kind of this other. In other words, there were basically kind of two things going on. One is how things are arriving, and then how we deal with them once they do arrive. And so the other thing is that when you look at stuff like this particular pattern was one that kind of comes up a lot. We've already seen several versions of just that structure. And similarly, this structure right here, this an event that kind of keeps repeating itself, that's another one that keeps showing up. And what that suggests very strongly is that what if we could kind of pull these apart and make them separate things? That would be great, but how do we get them to work together? And that's where this sim event listening thing comes in. So what sim event listening is about is that, well, listening, when you're listening, there's a speaker and a listener, or a source of a message and the receiver of the message. And this is kind of how it is represented. So each of these boxes now is an instance of an event graph, an instance of an event graph. And the way that the meaning of this is that whenever some event in the source gets executed by the event list, if the listener has the same event, then it automatically gets triggered. In other words, it's like, you can think of it like resonance. You know how, like if you have a stringed instrument and you kind of play one of the strings and the other strings have resonance. You get that? Or okay, so here just as to make it a little more concrete. I mean, this is kind of abstract, but we'll do a concrete one in just a moment. So so here's an event, a little snippet of an event graph, and here's a snippet of another event graph. So, and the way that it works by default is that everything gets multicast, as it were. So so at some point, event A is going to get executed by the event list. When it does, it's going to schedule B and it's going to schedule C. So now when B occurs, it's going to be heard by this guy. And he's going to say, oh, I just heard an event called B, and I've got a B. So I'm going to execute my B, and that in turn will schedule this event D. And sometime later, this event C will occur back here. And this guy will actually hear it and say, okay, I just heard an event C, but I don't got a C. So I'm just going to blah, 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 blah. I'm going to stick my fingers in my ear and say, I didn't hear that. So here's kind of how that kind of looks. So when event A occurs, it will schedule B and C. And then when event B occurs, then the listener is going to hear B and then schedule D. And when it hears C, it's going to hear C, but it's not going to do anything. So here's a simple example. Like supposing, okay, remember that you've all implemented an arrival process and written it, it's a class. So one of the translations is an event graph, and we're going to start calling them event graph components, but an event graph component translates into a class, whether it's in Java or in Python. And as a class, I can instantiate as many of those as I want. So what if I'm now in this situation? I have two arrival processes going. And they may have entirely different mechanisms for their inter-arrival time, to say entirely different distributions. And I don't kind of know or care about those, but what I want to do is I want to count the total of all of them. Now, an activity as simple as that is well, if I get a bunch of them, I can just sort of add them all up. But the programmer virtue of laziness says I don't want to do that. The virtue of laziness says, why do I have to do that? I'll have somebody else do, I'll have the computer do that. I'll have a model do that. So what I can do is I can write, I'm not going to call it arrival listener, I maybe call it arrival counter, whatever. And so here's the arrival listener has one state variable. I'm going to call it H. Why do I call it H? I have no idea. But it has a run event, and its run event is going to initialize at 0. But every time it hears an arrival from whoever, it's going to increment that number. And so it's going to do the counting for me. Okay. Now, here's the maybe I should do the whole stuff here. So can everybody see my net? Okay, I'll do it. If you do a pull from the class code, which I have not yet done here. So what does that look like? You again right click at the top of the project, git remote. Hopefully I won't have a problem with this. And see the little blue U, that means that it's going to be updated. And here's the arrival listener. So we saw the arrival listener just has a run and an arrival. So I'm going to call it total number of arrivals. That's what I was calling H. It doesn't have any parameters, so I can actually just stay with the 0 argument constructor because there are no arguments to be done. But actually the run method doesn't actually schedule anything. So in this particular case, the only piece of the run method I need is the reset method, which initializes my state variable to 0. And now I just write an arrival method corresponding to the arrival event. And what does it do? It simply increments the total number of arrivals and then fires the property change. So how do, so, so here's that. So in my main method, okay, here I'll create two. So I'll do them as an array. So I'm going to get an array of random variates, and one will be a Poisson and the other will be uniform. Okay, so two different arrival things. And then now I'll create an array of arrival processes, and each one will have the corresponding inter-arrival time, and just a for loop here. This is the main method. So in the main method, I'm allowed to use for loops and other kind of stuff. So that's, but in the component, I'm not allowed to do that. Okay, so then I'm going to dump the properties. Here's my arrival listener. I'm just going to instantiate it, and then here's how I tell it to listen. So the for each of these arrival processes, I say add sim event listener to my arrival list. What I'm calling my arrival listener. So I add sim event listener. That means that tells this object to listen to this guy. And I'm also going to do a property change listener. So those are the two different listener types that we have. So in fact, you've already seen the property, the property change listening, as it were. What's powerful about that is that in the next assignment, you're going to be using that to collect statistics. So that's, and then I'll sort of print these guys out and then just kind of run it in verbose mode. Okay, so what does this look like? This will, okay, I ran it for like 10 units. I always print them out because if I screw something up, then I'm not going to see my parameters here. So here we see the only run events are for the two arrival processes. The arrival listener doesn't have a run event, so there's no event to be doing there. However, when I do a schedule reset, that reset gets called, and we'll basically kind of see that once things, well, so the run event for the first arrival process says number arrival 0, one for the second one, number arrival 0. The thing about the run events is the run events are not dispatched, just because each component has its own run event, so that doesn't get multicast. Okay, but here's our first arrival. Turns out to be our for the and so here's the arrival process says there's now one arrival, and the total number of arrivals is now 1. Now the next one is okay, that was for the second arrival process. Now we have this one, and it has the first one. It goes from 1 to 2. And then you see how the total number of arrivals is just kind of keeping track of all these, even though it's not scheduling any events. It's just hearing them, just responding to them. And so, at the end, we finally stop. But then at the end, there have been 4 arrivals from the first arrival process, or I'm sorry, 5 arrivals from the first arrival process, 3 from the second, and a total of 8. So hopefully that's correct. So that's how you implement this. Now for the Python folk, it's kind of the same thing. Let's see, got to make sure do a pull. Hopefully I don't have a conflict. So in yours, in the student ones, it's called components. For this, it's called MV3302 classes, just to make sure that they're so different that there's no confusion. But similarly, where is it? Okay, so here's the arrival listener. Is exactly the same formulation. So here's our constructor. We initialize the total number. I'm calling it total number of arrivals. We initialize it to NaN in the constructor, but then in the reset method, we initialize it to 0. Here's the arrival method for the arrival event. And then all it does is increment the number of arrivals there. And so the test is kind of pretty much the same. So I create two, again, I'll use arrays as well. So I get a Poisson and a uniform. I instantiate the arrival listener. And here the simple property dumper in SimKit is called the simple state change dumper. Why? Because I think that's a more descriptive name. So now I'm going to loop over all these, instantiate the arrival processes. And add a state change listener to dump the state changes. And the sim event listener, my arrival listener, is going to listen to that. And then I'll list, I need to add it to the arrival listener as well. So when I run this, give me the, okay, pretty much the same thing. So just verifying that the arrival process, Poisson, uniform, etc. So we have the two runs. And then, so the number of arrivals for the first guy, or actually that's the second one as well. And then there's 0. And that's the one for the stopper event. Okay, so here we have an arrival for one of them. The total number of arrivals is now there. We have another one, and then it just kind of keeps going. And then at the end, here, when we run it on this, because the random variables are different, the totals was 9 instead of 7, but that, you know. Okay, so that is this example. Now, I actually do have a few more minutes despite that. Okay, so here's a more useful application, is that now instead of to implement the multiple server queue, we're going to use something called the simple server component, and it's just the server piece of the model. And what it's going to do, it's going to listen to an arrival process and just here respond to arrival events. And so now our simple server component doesn't need the inter-arrival times because that's going to be captured by the arrival process. So all I need is the service times and the number of servers. And so for this, I'll have the number in the queue, number of available servers, and then I'll count the number, the service completions as well. So the component looks like this now. So the run event actually doesn't schedule anything. Why? Because it's waiting for that first arrival from the arrival process. But everything else is exactly the same. So all run has to do in this case is initialize our state variables. The start service and end service, all this is exactly as we've already done, except the piece that's now not included in this is the arrival process itself. And so the way that they listen to each other is we have an instance of the arrival process and an instance of the server, and sort of to just kind of expand that. Here's our arrival process, which is identical to the one that you've already created. And we can now simply have our server component, our simple server component, listen to that. So whenever an arrival event occurs, it will be heard here and then kick off all of these other scheduled events. And what's powerful about this is that, and we're not going to do that, but hopefully you can imagine, what if the arrivals actually, what if there were actually two different streams of arrivals coming in with two different distributions? In the original model, we would have to go in and edit that model to add the additional stuff. In this, we don't need to do that. All we need to do is that if I had another arrival process that was doing the same thing, all I would need to do is instantiate it and have my component listen to that, and then all arrivals would just be processed. And this is assuming that they're all more or less the same. So, and what's the benefit of that? Well, I mean, instead of having to edit a bunch of, anytime I can just instantiate objects I already have and just hook them up instead of writing new code, writing new components, that's a win. It's what's called reuse. Okay, so, and that's the model I'm going to ask you to implement for the next time. So, and just as a reminder, now tomorrow, the 11 o'clock will be the lecture, 1 o'clock will be the lab. The 11 o'clock will use the lab Zoom link for those of you zooming in. The 1 o'clock, you can zoom in if you want. If you want to show up here, I'll be here, but it's up to you. Okay, so any questions? Any questions from the remote? Okay,